Hello Vulkan developers and welcome to Vulkan Performance Day. Today we're diving into the raw power of this graphics API for developers who crave speed, control, and maximum performance. Whether you're building a AAA title, a game engine, or just curious how to use Vulkan to squeeze every ounce of power from your GPU, this video is for you. Now, performance is a huge topic and you can optimize your engine in multiple ways on different levels. Today's focus is going to be the Vulkan command buffer submission mechanism. If you've been following my tutorials, then you know that this mechanism is handled by the VulkanQueue class. The usual sequence is to acquire an image, submit command buffers for it into the queue, and then present it. The submit async function is the faster method because it doesn't wait for the command buffer to complete execution. If you need to wait for completion, then use submit sync. At the end of the present method, we have a call to queue wait idle, which basically causes the caller to stall until the queue is empty of command buffers. This is the frame rate that we can achieve in this setup. But the call to the wait idle function is just a workaround, and if we remove it, we can see the frame rate going up, while the console shows some warnings that the semaphore must not have any pending operations. Obviously, something is not working correctly, and the purpose of this video is to fix the problem while maintaining the higher frame rate. Before we get started, I'd like to say a big thank you to Ivan, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev or by joining the YouTube channel as a member. The first step in any performance analysis is to make sure that we are doing the measurements while the system is in the best shape for it. For example, always measure in release build. In debug build, the compiler optimizations are usually turned off to make it easier to step-by-step decode and examine the values of the variables. In addition, the compiler automatically initializes the variables and adds implicit boundary checks to help you trap those nasty off-by-one bugs. In release build, the compiler optimizations are enabled and all those extras that the compiler adds to your code on its own are skipped. The next item is Vulkan specific. If you remember, Vulkan has several presentation modes that control the behavior of the presentation engine. Our preference was to use the mailbox mode and fall back to FIFO if it was not found. For the measurements, we're going to use immediate mode, which is supposed to provide the highest frame rate. In this mode, the vsync is disabled and the latency is kept as low as possible. I'm not sure that in any case and any workload, you will see a clear advantage to immediate mode, but since this is the recommendation for cases like this, I'm going to follow it. Of course, this frame rate is not normal or desired, but it makes it easier to detect even minor improvements. And finally, you need to set up the measurement itself. Since we're measuring frames per second, I capture the current time using GLFW at the start of each frame, calculate the delta from the previous frame, accumulate the delta, and check whether 1 second has passed. When that happens, the number of frames in this second is written to the console, as well as the title of the window. The counters are then reset for the next second. The advantage of using GLFW here is that the same code can be used for Windows and Linux. Let's see a high-level view of the system. We basically have 3 players. The CPU, which submits command buffers for execution and instructs the GPU to present the image. The execution units on the GPU, which actually run the shaders and write into the image. And finally, the presentation engine, which takes an image and puts it on the screen. Synchronizing these elements is the responsibility of the developer. We have to make sure the execution units use an image for output, which is not currently being presented, and we also have to make sure the presentation engine takes only an image for which all the command buffers have already been executed by the execution units. In addition, the CPU or the application must ensure that the resources are not reused before they are actually free, and it must avoid overwhelming the GPU or the swap chain. By the way, a VulkanQueue is simply a software abstraction for the physical execution units of the GPU. Remember that the VulkanQueue class maintains two semaphores. One to indicate that the image can be rendered into. This semaphore is provided to the acquire next image function, and then again when submitting the command buffer for execution. The presentation engine signals this semaphore when it is done reading from the image, and the execution units on the GPU wait on this semaphore before they start writing into the image. This handles one half of the synchronization issue between the execution units and the presentation engine. The other half is handled by the second semaphore. This semaphore is provided to the queueSubmit and queuePresent functions. The execution unit signals this semaphore when they finish rendering into the image, and the presentation engine waits on this semaphore before it starts presenting the image. It's important to know that the semaphore in Vulkan is an internal GPU synchronization mechanism, meaning that it can only synchronize between the different parts of the GPU, such as the execution units and the presentation engine. So the application is responsible for management of the semaphores in terms of handing them out to the different API calls, but it cannot signal them or wait for them directly. To reach the maximum performance level on a given system, we want the GPU to be always busy executing shaders and presenting images without waiting for the CPU to provide more work. And we want the CPU to always have an image available for work submission without waiting for the GPU to release an image. We accomplish that by maintaining a small queue of images, usually no more than 2 or 3. They represent the frames in flight. The CPU acquires images from the queue and submits command buffers for them, and the GPU executes command buffers and presents each completed image. We will probably end up with one party waiting for the other, but if the required frame rate is achieved, then this is okay. Now let's dive into the problems in the current implementation. The problem with the VulkanQueue class is that we have a single pair of semaphores. This means that we cannot have multiple frames in flight because multiple images cannot share the same semaphore. The solution seems simple. Allocate a pair of semaphores for each image. However, it's not that simple. If we remove the call to queueWaitIdle while utilizing a dedicated pair of semaphores per image, the CPU will run ahead blindly and submit work to images that are still in the process of execution or presentation. The result will be image corruption, undefined behavior, or even crashes. This is where fences in Vulkan come in. They enable CPU to GPU synchronization and allow the CPU to wait on certain events. Several Vulkan API functions take a fence as an optional parameter. The one that we will be using in this implementation is queueSubmit. Providing a fence to this function allows us to wait until all the command buffers in this queueSubmit function call have finished executing. Here's how the solution is going to work. The class now contains two vectors for the same pair of semaphores as before, image available and render finished. In addition, we have a vector of fences and a rotating frame index which goes from 0 to the number of images -1 and then back to 0. During the initialization of the class, the two semaphore vectors are resized to the number of images, and the wrapper function createSemaphore is used to create each element, same as before. We also resize the vector of fences for the number of images. Okay, so we have two semaphores and one fence for each image. We use the function createFence to create the fences. Notice that in the fence createInfo structure, we indicate that the fence must be created in the signaled state. Let's see the changes in the acquireNextImage function. We start by waiting on the fence for the current frame index. When going over all the fences for the first time, this will have no effect because the fences were created in the signaled state. From the second time and on, we will wait until the previous command buffer submitted using the same fence has finished executing. This creates the CPU to GPU synchronization that we are looking for. If the CPU is much faster than the GPU, we will often hang here until a previous frame using the same synchronization trio has finished. If the GPU is much faster than the CPU, then chances are the fence will already be in a signaled state by the time we get here, so there won't be an actual wait. After waiting on the fence, we have to reset it back to the signaled state. This means that if we wait on it immediately, we will block indefinitely until someone releases us. This will become clear in a minute. Next we call VulkanQueue and provide the image available semaphore of the current frame. Same as the fence. Now we don't know whether the image index returned by Vulkan will correspond to the frame index, which goes 0, 1, 2, 0, 1, 2, and etc. And in fact, we are specifically not allowed to assume that. But for now, let's assume that the image indices are provided in order, and later on in this video, we will take care of the case when they are not. So we can simply return the image index, and this function is finished. Next up is submit async. The wait and signal semaphores are set based on the current frame index. Okay, previously we had a pair of semaphores, and now we have a vector for each type. The function queueSubmit is called with the fence which we have just reset in the last parameter. We can now go ahead and wait on this fence, and it will be signaled when the command buffers in this call finish executing. We hope that by allowing 2 or 3 frames in flight, the fence will be signaled by the time we try to reuse this frame. Finally, we have the present function which calls queuePresent on the corresponding render-finished semaphore. Before we leave this function, we have to increment the frame index and reset it back to 0 when we reach the number of images. The next call to acquire next image will use a new set of semaphores and the fence. Now let's go back and handle the case where the acquired image is not the expected one. For example, we have 3 images and the swap chain returns 0, 1 and then 1 again instead of 2. In the current implementation, the frame index will be 2 on the third call, which means we will associate a new set of semaphores with the same image. Probably not good. The solution is to maintain a second vector of fence handles for the same number of images and initialize the elements to null. Okay, no new fences here. This is simply a reference to the original fence vector, and you can do the same thing using an array of indices. After we acquire the image, when we actually know the image index, we copy the fence handle of the current frame, the one that we waited upon at the start of this function, to the new vector using the acquired image index. Before we do that, we have a piece of code that checks whether this location is not a null and whether the fence in the new vector, based on the acquired image index, is different from the one of the current frame. The first check is simply for the first time we go through the fences. The second check will be triggered when the swap chain goes out of order. In that case, we wait on the fence based on the acquired image index. In the example before us, it means we will wait for the fence of image number 1 on the second time in a row it is acquired. So we have 2 waits in this case. one for the image we expected to use, and one for the image we actually got. Either way, the two sets of sync objects are now available, and we can safely continue. Now I have to admit that by default my swap chain always behaved in order, so I wasn't able to test this code under normal conditions. Therefore, I told the swap chain to allocate only 2 images while creating 3 sets of sync objects in the queue. This triggered a special case on many of the calls to this function, and I was able to verify that it works correctly. And that's it for today. Let me know what you think of this implementation and whether you were able to solve it differently. Thank you for watching, and I will see you next time.